What if I told you that this paper-thin device, about the size of a quarter, could power the world? You'd think that I was joking. Because I am. This isn't powering the world at all, anytime soon. Oh god. Now, while this little device won't be powering any cities anytime soon, it can generate electricity. When you apply pressure to this device, it'll make enough electricity to make this little light glow. Now, if you're anything like me, you might be wondering, how is this possible? I think it's magic. No, I'm joking. What's actually going on here is an effect called piezoelectricity. Piezoelectricity is when a substance becomes polarized due to the application of mechanical stress. When you apply stress to the material, it generates a slight positive charge on one side and a slight negative charge on the other, creating a flow of electricity. The effect works in reverse too. If electricity is applied to the material, it will change shape, which can cause a vibrating motion. The piezoelectric effect was discovered in March of 1880 by two French brothers named Pierre and Jacques Curie. They discovered that by applying pressure to certain crystalline materials, the material would generate an electric charge. Now, only some materials are piezoelectric. These materials are either made of crystalline structures or certain ceramics. There are also polymer piezoelectrics. In this video, I will mainly be discussing quartz. Quartz is a crystalline structure, which is a structure that is made up of a uniform and orderly arrangement of atoms. Not all crystalline structures are piezoelectric though. For example, diamond is a crystal, but it's not piezoelectric. Same with table salt, NaCl, but it isn't piezoelectric. So you can't just... Unfortunately, table salt doesn't have any piezoelectric properties. There are many piezoelectric materials, such as lead zirconate titanate, barium titanate, quartz, Rothschild salt, and even sugar. But for a material to be piezoelectric, its crystal structure must not contain a center of symmetry. This can be understood when looking at a crystal's unit cell, which is the smallest structure of atoms that you need to repeat in order to form a crystalline structure. For example, let's say these Cheerios and Golden Grams represent the different atoms in a crystalline structure. If the structure of the crystal looks like this, then a unit cell of the crystal would look like this, because it is the smallest amount of atoms that you can repeat to make the crystal structure. Now this is what a quartz unit cell looks like. Oh my god, how am I going to explain this? If we cut the quartz unit cell in two and put a mirror down the middle, it does not reflect what is actually on the other side. This is because the quartz crystal is asymmetric. No matter how many times we angle this, bend this, or turn this, it is not going to reflect the actual image of what is on the other side. Now this is a simplified version of the symmetry of a quartz crystal, so if you want a more detailed explanation, I've linked all the sources I used in this video in the description below. Now let's look at a model of quartz's crystal structure. Here we can see a structure made up of silicon and oxygen atoms. Now there are many different ways to view this structure, but there is one particular angle that we are looking for. It's this angle right here, and specifically this sort of hexagonal looking shape here. But let's look at a more simplified version. We can see this part of the structure is made out of silicon atoms with a positive charge and oxygen atoms with a negative charge. When the crystal is compressed, something called a dipole moment forms. A dipole moment is a separation of charge, or in other words, the charge isn't balanced across the crystal because there are more negatively charged oxygen atoms on one side. Normally, when the crystal isn't compressed, dipole moments cancel out because there is the same amount of positively and negatively charged atoms on either side. But when the crystal is compressed, there are more oxygen atoms on one side, giving it a slight negative charge, and there are more silicon atoms on the other side, giving it a slight positive charge. If you connect a wire to one side of the crystal and a wire to the other side of the crystal, you get electricity. Now you know why crystals like table salt or diamond are not piezoelectric. Table salt's crystalline structure is way too symmetric. When it's compressed, there is no dipole moment forms because the charges immediately balance out because it's symmetric. Diamond isn't piezoelectric because its crystalline structure is only made of one atom with one charge, and so there can't be a dipole moment because there's no difference in charge. Everything in that structure has the same charge. Piezoelectric crystals are used in many types of devices. Lighters, microphones, printers, watches, medical devices, telescopes, microscopes, speakers, sonar equipment, etc. All can use piezoelectrics. Many different fields of technology already use piezoelectric crystals, so while they won't be powering the world anytime soon, they kind of already are. If you have any more questions about piezoelectricity, then comment down below. And if you enjoyed this video, then consider giving it a thumbs up and also subscribing. Subscribing is free and it helps me out a lot. Thank you for watching, and I hope you enjoyed the video. Peace. Piezoelectric.